Hello. Hi. So welcome back. We would like to start the afternoon session. My name is Kosuke Ito, working at Kyoto University, Japan. Afternoon session begins with, thank you very much, the keynote lecture by Professor Chieh, National Taiwan University. Let me briefly introduce him. He obtained PhD degree with the supervision of Professor Kerry Emanuel in 1993. And after his works in NOAA, he obtained his faculty position in National Taiwan University. And he is, of course, famous for various kinds of works related to tropical cyclone. But one of the famous works is a dot star project and also secondary iwtrc formation related studies. I myself was a postdoc of him in 2011 and 2012. Actually, he was very generous and energetic every time. And actually, in his group meeting, every time he prepared food, sweets in a group meeting, and we enjoyed with the conversations. In such a kind of a free atmosphere, we enjoyed our talk, and then we developed collaborations. Okay, so I'm very definitely looking forward to his talk that covers his work, I think. So his talk title is The Roles of Wind-Induced Surface Heat Exchange in Secondary iwtrc Formation, Rapid Intensification, and Size of Tropical Cyclones. Okay, please.
Good afternoon. It's truly my honor to be here. And I would like to thank the organizers for having this wonderful workshop here in Yokohama. And thanks for the introduction. Very nice introduction from Ito-san. And actually what he mentioned about the nice sweets during the group meeting was originally the idea from Kerry when I was a student at MIT. During our group meeting at that time in the early 1990s, we usually would have donuts and coffee together with Kerry. So I would like to take this opportunity to thank Kerry again for that, for the inspiration. Well, I would like to take this opportunity to talk about the role of the Wishi in SEF and RI and size of tropical cyclones. And these are a series of works conducted over the last 10 years with my students, including Yishen, Huang, and Jiren, Chen, and Qinpeng, Qinxuan, and also Li Zishen, and some of other members of my group. So, and these are my outlines. So before I start, actually, I would like to refresh you with a nice, memorable photo taken 4 years ago. How do I continue? Oh, this one. Yes. So, anyone in this photo, please raise your hand. Thank you very much. Okay. Any one of you not in this picture? Oh. What about the others? Well, thank you for coming to this new place as the Center of Typhoon Research for the Future based in Yokohama. So it's nice to be here with all of you together here for this meeting. So let me continue my talk. Well, as we all know, in this very morning, Kerry gave a very inspiring talk about partly about the genesis issue, but mostly about the hurricane risk. So I chose these different topics about the forecast of intensity. As you can tell here that, the track forecast errors has been reduced dramatically over the last 30 or 40 years. But on the other hand, on the right-hand side, the track forecast or intensity forecast has always been very limited progress. And there are many different processes involved in affecting the intensity evolution, as shown in this review paper by Yuqin and myself, and including the internal dynamics, environments, and also the boundary layer processes. And of course, today I may put more emphasis on the intensity change associated with SEF and also the role from the surface fluxes that will involve the so-called Vichy. And there are about 6 papers I'll try to review. Perhaps I can do the first 4 parts of the papers. And the first one is about the unbalanced dynamics in SEF, as Ito-san already mentioned earlier, based on some of the earlier observations we did 14 years ago. And that led to this very interesting findings. And later on, actually, after this work, there was 1 year, I had some discussions with Carrie during the hurricane conference in the US. And Carrie asked me, what about the feedback from the surface on this problem? So I started to work on this issue and then come up with the following few works about the role of Vichy in SEF. And later on, the same student did the work for investigating the role of Vichy in the rapid intensification of tropical cyclones. And more recently, about the impact of outer surface heat flux on RI and also on TC size. So let me address the first paper first. Well, let me give you the overall background review about the SEF. As we all know that for tropical cyclone reaching certain intensity, like category 3 or higher, they tend to have SEF. And even sometimes you can have also tertiary eye walls like this one, triple eye walls, as shown here. And generally after SEF, for about half day or 1 or 2 days, you have this ERC. And they would affect the intensity and structure on a time scale from few hours to a number of days. And this poses challenges to the hurricane forecast. And the second is about overview of RI, rapid intensification. Well, it was defined basically by this paper in 2003, Kaplan and DeMaria, based on the Atlantic hurricane data. They show that from the accumulation frequency distribution of all the Atlantic storms and of the intensification rate, and they put the top 95% percentiles as the threshold to define the rapid intensification. Basically, it requires the wind speed to increase about 30 knots or 15.4 meters per second in 1 day, or the drop of mean surface sea level pressure to up to 42 hectopascal in 1 day. And it has also been shown in their works for all the Atlantic tropical cyclones, and almost most of the storm with the intensity above category 3 or 4 and 5, almost 80% or even 100% of the strong major storms, they all experience RI at least once in their lifetime. And there has been also an interesting work demonstrated by Jiang Li, and showing that the distribution of the global tropical cyclones lifetime maximum intensity have this bimodal distribution, while many of the second peak here will be contributed by the RI storms. About more than 80% of them are from RI storms. Only few percent are from non-RI storms. And what is also interesting in more recent work, and some study has shown that the distribution PDF of this intensity curve may shift to the east further, with more reduction on this part and more on this part, which means that following the talk from Carrie this morning, the risk from the hurricanes or tropical cyclones can be even higher. And so understanding what happened for these RI storms is a very important issue. And also, as mentioned by Carrie earlier, we need to understand the basics or the physics of these processes. So another review is about the wish effect. This was also suggested and proposed by Emmanuel in the late 80s, about the feedback mechanism between the surface heat exchange or the surface heat flux provided caused the intensification of the storm, and that intensification further increased the surface flux. Such a positive feedback would lead to play very important roles for the growth and also intensification of tropical cyclones. But there are some studies from idealized simulation about 10 years or later by Montgomery et al. They show that, well, even if we kept the wind value in calculating the surface flux at certain thresholds, such as 10 or lower 5 meters per second, some of the idealized simulations show that the storms can still intensify, although at a lower intensification rate and with a smaller intensity in the later on. And this result can also be found in a study by Fuqun Zhang and Emmanuel later on. But another interesting case is that if you look at the real case, when there are asymmetric features, including the wind impact of vertical wind shear, actually, if you really reduce the feedback, for example, in this case, for the curve here in red by 5 meters per second, actually the storm cannot develop. And this indicates that, well, in the real case simulation, little development occurs when the wind speed is kept at 5 meters per second. So today I'm going to combine all these three topics together, from SEF to RI, and then the role of wish in those processes, based on the following papers. So let me start about this paper on SEF. And I actually briefly talk about the results of these two papers last year during the Emmanuel Symposium at MIT. Well, so first of all, let me quickly go over the mechanism that has been suggested about the plausible intrinsic mechanisms for SEF. Well, there have been ideas proposed about how SEF can happen. Well, one is about you have this vortex Rossby wave propagating outwards until the radius of the stagnation point, where you no longer have the waveguides, so the Rossby wave will stop and accumulate their energy there. That is the place where the perturbation energy would increase, and then you have the feedback to induce the new eye wall. And this idea, well, has been shown to, in certain cases, to be right, but also in certain cases to be not really suitable. And there are also other ideas about how the mode forms in the region of this wind profile, where you have very strong rapid filamentation zone. And in this region, that's where the mode tends to occur. There have also been ideas about how the axis symmetrization of two vortices, when they interact, can induce the suitable secondary eye wall. Although there are also counterexamples in different type of experiments. And there is also one interesting theory about so-called beta scale formation. It's called of axis symmetrization, BSA hypothesis. The idea is to make use of the idea of the 2D turbulence, and suggesting that they tend to favor to have the energy cascade, the turbulence energy cascade into a certain regime with the beta scale. And that selective scale tends to happen in the location, in the edge of this vorticity gradient. And that is the location where you tend to have the new secondary eye wall through the feedback from the Vichy. And there are also very popular ideas about how the outside rain bands or induce the heating outside. They can enhance the secondary circulation outside and in a region with higher inertial stability. And that balance the response to heating sources outside can induce the secondary eye wall. And despite all these potential mechanisms, I would like to propose another one that is related to the unbalanced dynamics response near at the top of the boundary there. And also, what we call the role of the super gradient winds in those areas. And as you can see, there are all kinds of different ideas proposed. But today, I'm going to review this first. Okay. This whole idea of the results is based on this experiment. And it's called T-Park. It's actually collaborating closely with Nakazawa-san in Japan at MRI at that time, and with other scientists in the US, Pat Hart and Jim Moore and Weissman from Germany. And the idea was using 4 different aircraft to conduct the reconnaissance and surveillance flight observation and to study actually the whole life cycle of tropical cyclones. But it happened that during the whole period, it was actually the first time ever in Western Pacific with so many flights observations available. In total, more than about 500 flight hours were carried out, and with about 1,500 drop-in sounds deployed. And it happened that Typhoon Sindaku was a case in point, right, located in this here. And it experienced some interesting structure change. And we therefore can use these aircraft data to reconstruct the structure of the storm evolution. And as shown here, Typhoon Sindaku in 2008. So it happened that there was about 2-day periods with 9 flights, 4 penetration flights from C-130. We were able to get the very detailed structure of the storm from the drop-wind sound deployed plus the SFMR observation from the C-130. So we therefore presented 2 papers on these topics. One is to construct this model consistent observation, consistent results for Sindaku, and then also investigate the unbalanced dynamics during this process. So these are the photos. These are the pictures of the flights by the Dust Star plus by C-130 at the same time, and these are all the drop sounds available during that period of time, and the conventional radio sound over the land. And we make use of this data with 9 flight missions, about 160 drop-in sound to construct this data set. And based on the methods we developed at that time using the ENCAV data assimilation originally proposed by Fuqin Zhang. And the key is that we assimilate this model with the data from the axisymmetric surface wind profile, like here. And the outside is from the Dust Star drop-in sound. And the inside is from the C-130 wind structure, partly from the SFMR, and the others are from the inner eye wall drop sound. And we do the update cycle to be able to produce this data set. Even though it was carried out at 5-kilometer resolution, conventionally, it is very difficult to produce the secondary eye wall with this low resolution. But with the help from the very good data sets we have during that 3-day periods, and actually with some ensemble members, we were able to produce the drop-in SEF process. And the results can be shown here that this is Hofmöller diagram, radius and time of the surface wind. And starting at this time, we started to see the buildup of the secondary peak of the wind, and eventually it take place of the inner eye wall and replace the inner eye wall and complete the eye wall replacement cycle later on. So we define this time as the secondary eye wall formation time, 0 hour. And we can also find very similar features based on the vertical velocity at 1 kilometers, or the PV fields, or the column rain rates in. And here's one pictures of the plane view of the potential vorticity at 1 kilometer height. We see it originally about 1 day before the SEF, you have these sporadic convections outside, but it gradually got organized and then eventually become a symmetric secondary eye wall at SEF time, S0. And later on, replacement happened, and then one single eye wall contraction again. And the results are very robust in all the 28 ensemble members we carry out, indicating this contraction earlier for the first 2 days. And then at this point, we have the formation of the new secondary eye wall and replacement later on and contract again. So I'm going to show the result based on the first ensemble members because all the rest are about very similar, produce very similar results. And this is an axis-symmetric view of the structure of the storm in radius and height. So as I just mentioned, about 1 day before you have one single eye wall, and then contraction as it's contracting is also expanding, as you can find here. So the tangential wind is extending outward in the lowest 2 kilometers, and as shown here and here. So overall, we see this very strong precursors prior to SEF about the expansion of the outer swirling circulation above and just within the boundary there. This is about the time finally the new eye wall forms right at this location. And if we also look at the mean absolute angular momentum in radius and also the radial flow in radius and height, well, the blue indicates very strong radial inflow. This is about 1 day before, until 1 hour before the formation of the new eye wall. And there is a very clear signature of the advection of this M, absolute angular momentum air inwards, by a very persistent and sufficiently large boundary layer inflow. And this inflow tends to move this M inwards, as you can tell here, this 3 line moves inside and 5 also moves inside. And this process tends to increase the tangential wind right in this location where the new eye wall forms later on at about 100 kilometers radius. So we use this, so we do the dynamical interpretation in this work by emphasizing the results based on this region. And the results shows that the key is to identify the gradient force, which is the difference between the outgoing centrifugal and Coriolis force and the inward pressure gradient force. When it is positive, that means the wind is supergradient. When it's supergradient, then we tend to have the acceleration of the radial flow. So it stops the inward radial inflow. So the result is that we have this increase of the supergradient flow in time from 16 hours before to the time when we have the secondary eye wall. And also, so other than the increase of persistent increase of the supergradient wind, and we in the same time see the convergence in the lower boundary layer, and also the increase of the vertical velocity in that region where the secondary eye wall forms later. So this whole picture seems to suggest that, well, again, if we do the momentum budget, which we did later on, a few years later, and it is also showing the increase, again, the increase of the AF. And if we also consider the friction effect, which is negative over the boundary layer, And so if we deduct the dissipation, we still see the overall deceleration of this U, or we say the radial outward flow acceleration. And that is also decelerating the air parcels in the inflow layer. So overall, it creates this convergence zone in that location. And in the meantime, if we look at the mean tangential momentum and the momentum budget for the tangential wind, we see a clear signature of the inflow of M, advection of the M. So this radial advection due to the mean flow increase with time within the inflow layer. And this is the main process leading to the intensification of the storm in that location. And the vertical advection tends to advect the momentum obtained in this boundary layer upward into this part of the troposphere, lower troposphere. So the overall result is a production of the tangential wind, not only in the boundary, but also above the boundary layer. And it can be shown that overall, the SEF can be interpreted as the region where we see the so-called supergradient winds in red here. So when we have only eye wall about 1 day beforehand, this is only one place with the supergradient flow pattern. And then during the transition process, we started to see the buildup of this new supergradient wind zone in this area until later on it became a real secondary eye wall. And then eventually this one was replaced, and then with only one single eye wall left. So overall, it is interesting to show that in these two papers about this idea of a progressive boundary layer path to secondary eye wall formation. And we show that this unbalanced boundary layer response to the expanding swirling flow is a very important process for concentrating and sustaining deep convection in a supergradient zone, where we start to see the formation of the new eye wall. Well, given the condition that all the other thermodynamic variables are available. So this is the idea of the first part of the work. Now let me move on to talk about the second part. After my conversation, actually some years ago, about 2015, I believe, during the 2014, during the Hurricane Conference, and Kerry asked me about this question. So I decided to do some investigation on the role of Vichy during the SEF process. Well, the idea is that, okay, here is the thought experiment. Well, because it is the expansion of the tangential wind is a very important precursor. But we know that during this process, it tends to pick up more surface heat flux. So potentially, there is this positive feedback should play some roles for the process of SEF. So we decided to take a look at these problems to see how the feedback from the Vichy on the expanding swirling wind, as shown in many different observation or numerical studies, that can impact the secondary eye wall formation. So here's the design of this work. Again, we run the same model again, but this time we don't do any data assimilation. We just let the model does its own work. But at 5 kilometers, they cannot produce secondary eye wall. But if we increase the model to higher resolution, in this case, 3 times up to 1.7 kilometer, then it leads to the secondary eye wall formation, almost identical to the one we got at 5 kilometers with very intense observations. So here is the results from the control experiment with this natural model simulation without data assimilation. Well, we have this again in the first, at about SCF time is happened is 32 hours after the simulation. And then again, the replacement cycle occurs later on. And what we see is that we have this signature of the expansion of the tangential wind near the surface. So that's similar to what we already described as the expansion of the swirling circulation. And at this point, we also, if we look at the vertical velocity also show the very similar features. And also, if we combine the vertical velocity with the cape available, we see that there are a lot of cape available outside. But when the convection started to happen and focusing on in this area triggered by the increased large scale vertical velocity, and it released the cape and increased the wind speed dramatically in this region and with higher vertical velocity later on. And the results can also be shown from this diagram indicating not only the wind, but also the heating. And as we can tell here, much stronger heating later on associated with the new eye wall. But during this process, I'll take this difference between the 32 hours when SEF happens, the difference between this time and this time. And if we look at the difference between these two times, we see a significant increase of the inertial stability outside in this region. And also the increase of the potential vorticity in this region during this period. So it's the development of the high inertial stability air over that area that should be fallible to build up facilitates the heating efficiency and enhancing the tangential winds by enhancing the secondary circulation feedback in that area. And the same results as to the control experiment is also to see the impact of the increase of this new region with super gradient flow right at the location where the new eye wall forms, as shown here and later here. And we also see stronger inflows in the boundary layer that can be found in also this simulation. So we decide now to take a look at the sensitivity experiments by constraining our heat flux from the surface. So in other words, we try to suppress the feedback from the wind by suppress the wind speeds in calculating the surface heat flux at certain wind speed from 15, 10, 5, all the way to 1 for different type of setup. But we also design experiments to see the impact of the region of the suppression of the feedback. And one is we call the suppressed areas about everywhere outside of the primary eye wall, or everywhere only inside of primary eye wall, or everywhere but outside of the primary eye wall, maybe further out, it's about 80 kilometers. Or in between, we only suppress the feedback from this region. We try to understand whether the region plays very important role for this particular SEF process. Here is a simple summary of the results. Well, with the shape of the blue indicates the region where the suppression of the heat flux were covered. Well, for the control here, this is the typical SEF process of the tangential wind development and vertical velocity. If we only suppress the heat flux in the original eye wall region, actually the storm becomes much weaker inside. However, what is available outside can continue to grow, and eventually a new eye wall would still happen. And the final intensity actually were decided by the new eye wall. It has not direct relation with the weakened first primary eye wall. This is an interesting result. And on the other hand, if we constrain the outer feedback or the suppression of the heat flux with very strong very low threshold wind, only at 1 meter per second, well, the whole thing was killed. So nothing will happen here. But if we allow a little bit more feedback at 10 meter per second wind, and the secondary eye wall still can roughly form later on, but it's much weaker. So the idea we show in this 4 diagram is to find that around and outside the SCF region, the wind feedback appears to be very important. And what is inside, actually, in the inner core, the role is relatively limited for the secondary eye wall formation. So it's close to follow our physical intuition, but we have to go through the experiments to find out what happened. So if we look at the evolution of the wind speed at the surface, as I already mentioned, there are different experiments with different threshold. But no matter what threshold was used, once you limited the evolution of the secondary eye wall outside, well, even though the inner part remains still exists, but the intensity never pick up, it would not be able to catch the new eye wall. And then the wind, the final result of the wind is much weaker than the control experiments. On the other hand, if you only reduce the heat flux in the inner part, even though it's much weaker initially, but eventually the new eye wall will pick up the wind and the eventual wind speed will be very close to the control experiment. And these are the major findings from this part of the calculation. And then we also start to think about, to try to understand the processes by looking at different variables to understand what happens and to all different favorable processes from the cape, from the convection and heating and so on to the intensification. And the key from this diagram with all different type of experiments is that we see that when we constrain the wind by suppression of the heat flux further outside at very low wind speed constraint, then nothing is going to happen. So in this region, actually, you don't have much cape at all. And it doesn't have enough surface heat flux to moisten the boundary layer air. And it never have the chance to have convection development. And in this case, no SCF in the outer part, so no SCF. But for the other experiments, and the SCF can occur with different magnitude. But nevertheless, they were able to pick up the cape outside and eventually help favorable for the SCF at later time. And this is a little bit busy picture, but the key is, again, is to show that if we only look at the heating rate, the heating average at certain time of, right before the original formation time of the secondary eye wall, that we see very little increase in the heating rate in this part of the, where the secondary eye wall is supposed to form. As compared to other regions, then we see clear signature of the increased convection or heating rate. And this is also the same for the change of the inertial stability. And during this period of time from 22 to 32 hours. So there is small increase in the tangential wind or the inertial stability in this region, but eventually no secondary eye wall. But for other cases, we'll all see this increase of the tangential wind or the the inertial stability in different setup. And this can also, again, be shown in terms of the super gradient flow zone. And not here, but it was present in other places. So overall, we still can see the formation of the new eye wall associated with this super gradient zone in different setup, but not in this particular case when the wind speed is constrained. highly. So for this part of the work, overall, we have seen the results that, well, the original ideas for the SCF theory, we try to emphasize is one, through the feedback of the boundary layer or the so-called unbalanced dynamic process associated with the increase of the expansion of the tangential wind. There is a feedback right here that increase leads to the secondary IO formation. But there are also other features as been shown as the balanced response to the expansion of the tangential wind, as this expansion of the surface wind also increase the heat flux and the heating and also convection and eventually secondary circulation and further spin up of the vortex. So the operation of these two make SCF occur. But with the wish feedback, and they can work on both ways. But once this is suppressed, especially in the outer region, that really impact the formation of the secondary IO. So this is the second part of the paper I want to emphasize today. So now let me go on to talk about RI. Well, here is a very quick review about the idea of RI that this part I already mentioned. Is defined for Atlantic storms, and maybe it needs to be adjusted for Western Pacific ones. But we'll stick with this definition for our study here. And it has been shown that there are certain important processes or factors related to RI, from convective heating to the axis-symmetric secondary circulation and symmetric convective structure, or the role of the vertical hot towers or convective burst within strong updraft within the radius of maximum wind, and also the role of the formation of warm core plus the availability of cape or scape in the environment. And this has been shown by various different studies in the past. So we are going to combine all this together to see how the wish process affects RI. On the other hand, there's one interesting paper by Falco, Jude, and Chen. It's about the predictability of and uncertainty of RI. And in Jude's thesis work, he showed that, well, for Hurricane Earl, and in 2010, he conducted a series of numerical simulations, and he found that in his about 100 ensemble members that produce the RI, but they tend to be, the black curve is reality, observation. And the blue one is the one which has the RI earlier. But the red ones are the other 60% of the cases in the ensemble simulation that produce RI at later time. So there are two types of RI onset periods, totally different. So they show that because of the complex interaction among the environmental vertical wind shear, the mean vortex and then internal convective processes govern the TC intensification process that drives the very diverse pathways to the maturity and leading to different RI timing. And this essentially means that even though all these 91 ensemble members were able to produce the RI as in observation, but actually they are the predictability is limited because they happen not at the right time. And actually, there are two groups of the RI process. And there's another work from one of my students a few years ago. He found that actually, based on some results from observation of Razor and Rogers, he showed that if we only look at the very strong convection, we call the convective burst, but the signature is actually not very strong. But if you also look at the so-called weak to moderate convection as defined here, you don't need to have the 5 meter per second vertical velocity to define the CB. But if you look at the weak to moderate convection, which has the wind speed about 1 to 5 meters per second in the middle troposphere. And the signature is much higher. And it covers many more grid points that can be found in the analysis. And we think that this is probably a very more important precursors than only looking at the points of the CB. So in our next study, we also will take this idea as one of the importance index for our analysis. And there is also other work from Black showing that, well, you see that when you have the wind shear, the distribution of the convection and also the feature of the tropical cyclone can be very asymmetric. Usually in the upshear side, the convection is weaker, and there's more on the downshear side, especially in the development stage. And the results here from Rios Barrios also show that, well, in this particular RI process, actually the RI happens when this is the 4 different quadrants in this coordinate. And we see that there's very strong downshear left component of convection. But later on, when it's really getting organized, it wraps up, and then I occurs later on when it becomes fully axisymmetric. And that is the time of the real intensification. So this part of the works also shows the importance of the role of the vertical wind shear and the role of axisymmetrization of the convection before the RI. And there's another work from the observation of Rogers indicating that, well, before the spinning up of the vortices of the typhoon, and we see the expansion of the surface wind. And this can also be found here. So it seems that the RI also occurred before this expansion process. So it is natural to ask what roles did this expansion play through Vichy effect for RI. So that leads to this work 3 years ago about the role of Vichy in RI of TC. Well, this diagram slide is a bit busy, but the idea is that the second thought experiment is to try to understand the role of Vichy in RI. And basically, we know that, well, when the wind again is expanding, and we see the gradually increased vortex scale enthalpy flux to the development of the convection. And also that accompany reinforce the secondary circulation, resulting in the strengthening primary circulation and mid to up levels, which facilitates the formation of the mid-level warp core. And in the meantime, we see the strengthened I square, the inertial stability, and providing favorable environment for the onset of higher heating efficiency. And that would be very favorable for RI. And so all this also indicates the potential dominant role of weak to moderate convection in the onset of RI, as shown in this paper by Chen and Wu in 2017. And there are several favorable inner core conditions for RI, and which we will investigate later on today. One is about the low level theta E, and well, the presence of the convection and the feedback from the secondary circulation, and also the increase of the inertial stability. And these can be also related to the Vichy process. So that is something we want to evaluate in this work. So again, let's do a model experiments by doing the same study on Typhoon Maggie as in this paper in 2017, and at very high resolution, 1.3 kilometers. Of course, we removed the islands that was very close to Maggie at the later part of the integration. And we limit the wind speed at different threshold as done earlier. but we limit the wind, the feedback in the whole domain. So 4 different type of experiments from cap 20, cap 15, cap 10 to cap 5. So cap 20 means that all the wind speed above 20 meter per second on the surface would be reduced to 20 when doing the calculation of the heat flux on the surface. Here is one results of the evolution in time of the wind speed at 10 meter surface. And what we see here is that, well, the control experiment shows that, well, the RI occurs at about hour 21 here. And for the experiments in red, that is cap 20, it starts later, maybe around 6 hours later. But in pink, even later, 34 hours here. But in blue, when the threshold is kept very low at 10 or 5 and no RI, the intensity cannot continue to increase, or even it may decay for a certain period of time. And there are also certain period of time, as shown here in dash, indicating we call it rapidly, or we call it significantly intensifying period, where we calculate the increase of wind in terms of the 6-hour intensification rate, about 4 meters per second, which is 1/4 of the definition of RI for 24 hours. But so here we all see, after RI, later time, you see the SRI, the significantly increasing intensifying period. And for the results from the MSLP, it's about the same. So basically, there's no intensified RI for the blue simulation with the dramatic suppression of the heat flux or the Vichy impact. So now we decide to look at the detail of all the variables we mentioned earlier on. For example, first we look at the axisymmetric viewpoint and the mean vortex evolution. Look at the mean component, including the azimuthal mean tangential wind and convection, and the mean inertial stability and heating, and also the warm core, or the vertical mass flux and theta E distribution, and the secondary circulation. And we'll look at the asymmetric part later on. So here is the mean component of the evolution of the 3-kilometer vertical velocity in shades and the 1-kilometer tangential wind in contour. And what is clear is that, well, as we already mentioned, this is the RI starting time, 21 hour and 27 hour and 34 hour and never. And the basic idea we learn again is that when we have less suppression on wish, we see the earlier development of the eye wall and strengthening of the eye wall, and also earlier RI. And it's not only the tangential wind, but also for the vertical velocity. And if we look at the mean component of the diabatic heating in vertical profile in time versus the I-square, the inertial stability as defined here. And we see that, well, there is some increase of the heating right before the RI. And also it occurs here for these cap 20 experiments, but there is no clear signatures for the whole experiment in cap 10. And here we also see this heating becomes very broad, covering the whole entire column in the troposphere later on when RI happens. And with the increase of I square or the inertial stability in the experiments, in later time for the next 3 days. And so again, it means that more so-called wish feedback leads to more diabatic heating and increase of inertial stability. And we believe that the I square is needed it should be strong enough so the vortices would be able to intensify more quickly. But in this particular case, it never really increased. And this is looking at the delta theta E between the eye region with its outside environment, and the delta theta, and also in the eye. And as well as, here is only the delta theta. And of course, after RI, we see very robust increase of the warm core, and eventually covering the whole column in the eye. And slightly weaker, but still very strong increase of the warm core from few hours, maybe 10 hours before the RI, all the way to the development of the RI later on. But nothing happens when the wind speed is really kept. It has some small, very limited altitude of the warm core, but it's very weak, much, much weaker, only a few degrees as compared to up to 10 degrees in other experiments. And also, as we can tell, the vertical extent of the warm core is much stronger in the control experiment. When we suppress the Vichy feedback and the heat flux is not enough, well, the warm core will also be relatively limited. And here is another picture to look at the low-level theta E. And what we see is that when we don't have that heat supply enough heat supply from the ocean surface, and with the more suppression, and there's a huge difference in the theta E distribution near the surface. What this means is the prevention of the theta E decrease when you have less suppression of Vichy, and favorable for the development of convection and also keep, which I will not have time to show today. And this is another picture showing the vertical mass flux that also can be calculated from our model results. And the results here shows that when you have less suppression on Vichy, you tend to have more convective instability in the lower layer, and development of convection, and more steady and increase of vertical mass flux. So the red one all means the vertical transport of the mass flux, much stronger than the other cases. And for CAP 10, basically you don't have strong vertical mass flux. Instead, you actually have negative mass flux downward, which is not good. And this is another picture to show the distribution of the heating plus the absolute angular momentum surface contour, and also the inflow. And here we see the big difference among the different experiments at different time. But this is already after RI. But there is a huge difference in terms of the structure of the heating versus the inward transport of the M. So when you have suppression of the Vichy, you tend to have stronger secondary circulation. And that drives deeper inflow and spin up the vortex and leading to RI. And actually at that time, it's already RI. So one of the last few slides, we are trying to also to show the CB distribution plus the weak to moderate convection inside of the major inner eye wall region, about 80 kilometers inside, but not including the eye. But let's look at the results here. Well, the grid points of CB increase, well, as we can tell, from the CB distribution in counts of the grids from few 100 all the way to about 200. Actually, 200 grids is about only 1% of that domain within the inner 80 kilometer radius. Very, very few. So the CB is actually not a very good count about the active convection. It's very few. If you look at the relation of this CB count compared to the timing of RI, there's actually no very clear relationship. But if you look at the weak to moderate convection, where you have many more points with this 125 meter per second wind, as shown here. And roughly speaking, when we have this 4,000 grid points as the threshold, then I started for the black curve first. And then when the red curve reached 4,000, it's the second time I happened. And for the pink curve, it's also about the same when it reached about 4,000, which is about 20% of all the grids. And the I happened. And for the final one, the convection with weak to moderate convection associated with the blue curve actually remains below, most of the time below 2,500 and also less than 15% or lower, and they never pick up. And we think that is a very important feature that never catch up with enough heating through this moderate convection and leading to stronger feedback or circulation in direct circulation. And sometimes we can also look at the contour frequency by altitude diagram. The CFAT diagram shows that here we only shows the difference between the control and the difference control minus the cap 20 or 15. But overall, we see that when we have less suppression on wish, and we would have more active upward motions in red here. But in the meantime, actually right in the eye, you have also points where you have stronger sinking motion in the eye. And all adds up for favoring the development of the storm and deepening of the inner mean sea level pressure. So now let's move on to talk about the asymmetric convection and wind shear, and then the axisymmetrization of the structure. And we will also look at these features here. Well, first of all, we look at the condition at about few hours before the formation of the onset of RI. We already, actually, even during that period of time, after 10 hours of the suppression experiment on these 3 sensitivity experiments, you already start to see the difference of the storm structure. And the red, the purple indicates the contour of wind speed of 30 on the surface. And the blue is 20. And there are sporadic convections in the IWO region, but it's more organized and more axisymmetry right here as compared to others. It's more asymmetric. Here it's more symmetric. So with this in mind, let's continue to investigate the results. If we look at the plane diagram of the reflectivity at 3 kilometer altitude and versus the environmental wind shear, what we see is that, well, regionally, we see a clear signature of the impact from the shear. And most of the convection occurs in the IWO in the downshear side, and more to the downshear left. But they started to ramp up in time as the storm developed, and later on becomes fully symmetric, more symmetric. But for the experiment with limited feedback from the Vichy or the suppression of heat flux at different magnitude, we start to see more and more the asymmetric features never got chance to get organized. And there's a huge difference between this one and this one. And of course, and to this one is even weaker, and they never have the chance to become a strong or wind storm. And we also employ the methods developed by Miyamoto, Yoshi, and Takemi-san to define the axisymmetricity in W, vertical velocity. What we see is that if we only look at the lower levels, well, there is some difference about the axisymmetrization value. And it increased dramatically before RI from 0.1, 0.15 all the way to 0.25. But not for the other cases. And the increase of the axis symmetricity magnitude actually did not really happen until a much later time when the vortex really builds up and extend all the way up. So for the upper part to be more axis symmetric. And we also see the difference among the different experiments. And one big difference is that for the experiments in blue with very strong limitation of the surface flux, and it never pick up the value for axis symmetricity remains very low all the way from the beginning to the end. And here is another picture to look at this is the center of the stone, and this is down shear direction. So you have down shear left here, down shear right here. So if we do a plot for this, well, we clearly see very strong convection or eye wall in this region, DL, in the earlier from this is the Hofmöller diagram. So it continued to contract and intensify. But for this experiment for here, as you can tell, well, this is for control experiment. But even for UR, it picks up slightly later on, even though not as strongly as this one. But for other experiments with limited Vichy, you see that it's very bad, never pick up in this part. And for U-10, it's even worse. Well, so maybe I need to speed up because I'm out of time. Well, so the summary is that the study here shows that the Vichy could affect the TC involution, both in the pre-RI and during the RI stage. And it can also partly offset the negative feedback from the environmental vertical wind shear effect and leads to earlier TC axis symmetrization during both stages. So we come up with this very simple diagram indicating this process with this increase of theta E and K through the increase of the surface heat flux feedback, the Vichy, that really helps to develop this inner warm core and also the outer circulation and speed up the vortices leading to RI. And we think this is during this process, the Vichy plays very important role, especially when you have vertical wind shear. Well, because I'm running out of time, but I'll quickly go over the few extra experiments we have been doing over the past few years. This is the one we are about to submit this paper. So we also conduct several ensemble simulations. So we allow different variables to be perturbed with different ensemble members. And the way we did it follows the scheme we did in another paper. And in this work, so we were able to produce 3 times 5, that's 15 different perturbed initial fields. And for the control plus 3 different type of setup, we have 4 experiments. So in total, we have about 60 members. So let's look at what happened if we randomly perturb these variables. Well, actually, more or less, we see very similar results, showing that, well, with all these 60 different experiments, most of the experiment sets show similar results, meaning that the separation of Vichy leads to delayed RI with smaller final TC intensity. Same for the pressure field. And if you look at this diagram from 0 to 15 number and 4 different setup, more or less we see that you have a much stronger maximum intensity in the end for control and weaker storms and much weaker one when you have stronger Vichy. And maybe with one exception here, but I don't have time to come to that today. And we've done some analysis on that part as well. So more or less, more Vichy, we are going to have stronger maximum intensity. And we look at this interesting map. Recently, there have been people thinking about the RI issue in terms of it's really a problem of intensification rate. You want to look at the intensification in either 24 hours or 12 hours or 6 hours. And so we try to compare the difference of the results based on different definition of the intensification rate. And the result, well, if you are in this region, basically you have RI. And that's the control experiments mostly in this area. And it appears that we found that 24 hours is it's probably easier to look at the RI problems using 24 hours as the definition to see the change between the different wish suppression experiments. You can see clearly the difference among these four. But if you use very short time period, they tend to be all tied together. It's not easy to tell the difference. And we also see that there are different types of the onset time for RI. Some are earlier. Some members are later. So if we divide the groups into the earlier RI group as compared to late RI group, as shown here in blue and in red. And what we see is that, well, the difference among different experiments seems to be similar. But if we look at the structure, the initial structure actually in the earlier period of time was already quite different among these different experiments. These tends to be more axisymmetric earlier and also more compact earlier with stronger wind. And it seems that these earlier structure difference among our ensemble members already decide whether RI is going to happen in the same environment earlier or later on. And these are something we are still working on. So, well, finally, another interesting result is that this paper published 3 years ago, we show that, well, again, we do the suppression of heat flux again, but at different regions from no suppression to anywhere outside of the core and further outside and without the inside. So 150 kilometers outside, 180 outside, 240, 300 outside. Only the blue region is constrained. And with very high wind constraint, only calculation at 1 meter per second. Well, this is kind of thought experiment. And it turns out the result is very interesting and maybe consistent with our physical intuition. What happened is that actually, if you remove the inside vortex, and then it's going to be a very weak storm. But if you only remove the heat flux outside, actually the storm is going to be very compact and even stronger. So maybe this is something useful thought for the people who try to study the hurricane modification problems. When you reduce the heat really outside, it's actually not killing the storm, it's intensifying the storm for the experiments we show here. And of course, there are many analyses that can be carried out to address this issue. And you might be, if you are interested, please look at this work. And this is one of the picture showing that when you really limited the heat flux 240 kilometers away from the storm, actually you are going to have a stronger storm and more smaller compact storm inside. And final is about the TC size issue. It's also related to the wish feedback. And of course, also from the outside, which if you are interested, you can look at this paper. So I'm running out of time. So let me finish with this final. Well, there's no take-home message, but what I want to address is I try to combine based on the old observation and lead to some interesting finding of SEF. Then I decided to look at how the wish impact the SEF and RI and size in my talks today. And I hope that this information are useful to you. Thank you very much.
Okay, thank you, Chun-Chieh. So we still have 15 minutes for discussion. If you have any question or comment, please raise your hand or, yeah.
Thank you for very interesting talk. I'm interested in the secondary eyeball formation. So I remember that you showed the 4 panels of radial side cross section of the tangential wind tendency in your slide. So please show the slide. Maybe,
Sorry. Yeah. Could you ask continuously?
Okay. So, yes, I agree with your argument of the.
You mean the tangential wind change?
Yes, change.
Not this one.
No, radius side cross section of the. Yes.
You are talking about the earlier momentum budget?
No, maybe this, next two or.
I'm sorry.
Or before two. Yes, this one.
Okay.
I can see that the top left panel, even in the non-SEF case, local increase of the tangential wind. There is the increase of the tangential wind. So how does this? So I want to know the
why it didn't form the new eye wall. Yeah. Well, in this case, the increase is much weaker. It's about only maybe 20 or 30% of others. If the magnitude is on the order of 0.1 here and or 0.2 here, but in the other places, they are all about at least 100% higher. But let me go back to look at the wind profile to see what happened. It's all, the one I showed was all SC5. So that would be the case right here. Green, that's the case here. Yeah, it's really not picking up what's happening outside. So it never get a chance to, maybe at some stage it's good. But the difference we try to calculate here is based on 27, the difference between 27 and 32. That's during the period, right? Let me check. That's during this period of time, the difference. So it's really, in that region, there's really no major vorticity outside or major tangential wind outside. Yeah, I probably can take a look with you later on about what happened there, why they never pick up to have a new peak. But I think it's really much weaker. Yeah.
Yeah, I see.
Thank you.
Because in my understanding, the wishing mechanism is a type of the feedback mechanism. So if the mechanism is activated, we need to the contrast of the tangential wind in radius. Yeah. So I think that wish is intensification mechanism of the secondary peak of the tangential wind. So it might be different from the formation mechanism of the secondary peak of the tangential wind. How do you think?
Yeah, good point. Yeah, it depends on how you define the feedback. And of course, here, there are different experiments here trying to emphasize in these problems with only one single eye or only look at the maximum wind in that single eye wall. And there have been a number of studies still indicating that with limited heat flux, the storm can gradually pick up in the idealized experiment. But when you have you are not in the idealized environment, actually, there would be some maybe downdraft or drying effect or shear different type of influence that would limit, that will counterpart the intensification from the surface weak heat flux. And in that case, maybe the storm would not be able to pick up, I think. Yeah. So it's a balance or competition of this process, those processes, and that may make difference. Yeah.
Okay.
Thank you, Tsujino-san.
Any other question or comment? Yes, Minamide-san, please.
Yeah. Thank you very much for sharing your great work. And in your analysis about dividing those like convective bursts and like weak and moderate shears, it was very interesting, and I agree with you the importance of including weak and moderate shears, convections. But one question here is, I think, or I would imagine, the strong convective burst or convective peak is probably associated with the surrounding like weak, like convective region or like weak updraft region. So like I wonder, like how did you separate them, or how did you deal with those like
I
convective
believe there are some algorithms. We follow the work that has been carried out earlier by Rob Rogers. Let me get I'm sorry. Here. There have been different studies and showing how we define the convective burst. But when we want to look at the weak to moderate convection, not only we need to have the winning information, there's a criterion using the DBZ criterion, and with the combine these two, we select the region, the grid points with moderate to weak convection, and those were, I believe, that has been carried out by Rob Rogers in old days.
Yeah.
But here we try to emphasize that we believe that there's more signatures, the precursors from this part. And very difficult to identify this part beforehand. It's not very clear. Yeah.
I agree. Yeah. Thank you very much for sharing that.
Thank you. You can take a look of the paper to find out the exact algorithm we define to do this calculation that satisfies this condition.
Yeah.
Thank you very much. Let me see if I have that information right here. Okay. Yeah.
Any other question or comment? Yuchim?
Okay. So Junji, I think the carry also here, and we should talk about what's the wish. Wish is the feedback, right?
Yeah.
That's the original idea. Which is the feedback.
Yeah.
The tropical cyclone intensify and the wind increase on the IOR, and then it's flux of that's a positive feedback.
Yes.
But if the wind kept outside of the IOR, when the tropical cyclone intensify, the wind doesn't increase too much outside region.
Yeah.
So whether you still call this is a wish or not.
Yeah. These are hypothetical experiments for thought experiment to see how different regions of the feedback might affect the structure and evolution. But of course, the original definition or ideas of wish from Kerry was about, basically the positive feedback of the overall wind surface. Yeah, of course. Maybe it's time for Kerry to provide the answer for you.
Kerry, could you give some comment? Okay, no? Yeah, I myself think for example, some people compare CISC and wish, and I think it depends on a person. Different person have a different definition on CISC and wish, so sometimes confusing, right?
So it is, maybe we can switch the name from saying the suppression of the heat flux is in certain region to reduce the feedback. But if you want to argue whether that is called wish or the modified wish or sub-wish, whatever we have to ask Kerry's permission to use the words more correctly.
Okay, so any other question or comment, or the answer to that point is okay? So Yamaguchi-san, please.
Very nice talk, Gu-san. I'm also very impressed with a lot of great work from you and your team for better understanding of the mechanisms, SEF and rapid intensification. So there's many good studies in better understanding of the mechanism, but does it mean the representation of this SEF and rapid intensification in NWP model, especially in operational NWP model, also getting better? If yes, that's good, but if not, why? So so how, in other words, how the NWP developers can leverage the outcomes of these studies?
Yep. Very, very, very nice question, Yamaguchi-san. Yeah, you are still doing wonderful science after spending 2 years in Geneva for administration. But it's a big issue. I of course, I didn't know the answer about why the predictions or the current models cannot well capture the RI or SEF. But probably some do, but not always. That is something I don't know the answer. Of course, in this study, in the series of study, it's all trying to understand part of the physical processes involved. And hopefully we have a better understanding of this problem. But in terms of I show the work from Falco Jude, you know him in Miami. And his work appeared to suggest that the current, at that time, at this 8 years ago, the numerical models shows a very high uncertainty and for catching the RI under the same environment. You just do some small perturbations and see very different patterns of early RI or late RI with totally different evolution. So that says something about the limitation of the capacity in the model to really well predict this problem. Yeah, that's what I know. And perhaps we can see whether other people or Kerry can provide some insights on this problem, whether there's any chance that this prediction forecast can be improved through some specific design of the numerical model, or essentially it's a predictability problem. It's just beyond our capacity at this point. Yeah. What about? Yep.
Okay, Kerry, please.
Well, I think there's one thing that people who work on surface fluxes in tropical cyclones all agree on is that we don't know how to do the fluxes at high wind speed, period. Because you form these spray layers. We've tried to do experiments in laboratories, make measurements in real hurricanes. A whole Navy field project was devoted to that, and it's just the measurement problem is really, really hard. So we can talk about capping fluxes and so forth, but in reality, we don't know how to formulate fluxes at high wind speed, and it's something we really have to try to do as a community.
Harry? So those are also addressed here, but no solution yet. But Yi-Chun and I mentioned about this in our review paper almost 20 years ago. So we are still, I thought, well, later on, there are so-called Donnellan drag curve that is already better. It was kind of the product based on the lab experiment, but high wind regime, but there's no real observations from the reconnaissance flights. Not enough data collected for high wind boundary layer wind structure and the drag calculation. So this is part of not only the surface flux, but it has everything here. It's related. Yeah. So very sorry, Yamaguchi-san. We still have to work on this. Yeah. For some time. Yeah.
Okay, so we still have time for question. You have any question or comment? Okay, Shimada-san, please.
Thank you very much. Interesting talk. Yeah, perhaps my question is related to Yamaguchi-san's one. So I'm interested in case dependency on your on the mechanism of what you showed today. So you chose specific cases, Typhoon Meiji or Typhoon. I forgot the name. But how about
one is
other cases? Because you know, typical cyclones vary from case to case.
True.
Especially in the Western North Pacific, we have a lot of types of cyclones, and sometimes we see a lot of moisture transport into the tropical cyclone, or even small size tropical cyclone intensified in a dry atmosphere. So I want to know what's your thoughts about this.
Thank you, Uday. And I think, like the study that has been carried out by, for example, Falco, and they did Jude, they also did the real case study. But sometimes for idealized experiments, when it's very idealized, it tends to intensify quickly because the environment is favorable. As long as it's favorable, everything would just intensify. But in the real case, there are other complicated influence we have to understand. And for the SEF, because we started everything from Sindaku. So for the SEF, we think it's an ideal experiment, ideal case to continue the follow-up study. So we stay with Sindaku. But for the RI, because my earlier work also started with Meiji, so we continue to do the RI sensitivity studies based on Meiji. And also it doesn't have secondary IO issue in that case. And for the final talk, I study about the experiment is on Typhoon Sudiler. That's 2015. And that was because during the period of time, we find that was a case of typhoon very strong and very big. We want to study what happened there. So, but it's all by our own selection. It's not purely based on science. It's purely on what we have and what we are interested. So perhaps if some people are interested or we have time, we probably can explore some new ideas or different setups of experiments to further elaborate the problem. Yeah, Uday, thank you very much.
Okay, thank you very much. We are running out of time. So say thank you to Chun-Chieh for your wonderful talk. Okay, so we would like to have a break until 3:30. Any announcement from LOC?
Thank you, Ito-san, to